Electron configuration for elements. It's a periodic table shortcut method. It is the best method to know to be able to do these electron configurations. We have the different sublevels, which was covered in a previous video lecture. I want you to remember what is the maximum number of electrons that each of these sublevels can hold. Remember, S's can hold 2, P's can hold 6, D's can hold a maximum of 10, and F's can hold 14. There are specific areas on the periodic table that correspond to those sublevels. The S is located in groups 1A and 2A. P's are located over here in groups 3A through 8A. D's are in the transition metal area, and the F sublevels are located down here in the actinides and lanthanides. Isn't it interesting that on the previous slide there was a maximum of 2 electrons that S-shaped sublevels could hold? There are exactly 2 columns that represent the S-shaped sublevels. All of the elements that are in group 1A will end with the S1 sublevel. In group 2A, this is where it fills the S-shaped sublevels up, S2. If we look over here at the P's, there's a maximum of 6 electrons that can be held in P's, and there's exactly 6 columns over here corresponding from P1, P2, all the way up to P6. The entire column will end with P6. Let's look in the D areas. We said that they could hold a maximum of 10 electrons. Each of those columns are going to be labeled D1 through D10. I would recommend that you also label your periodic table in this format. F's then are 14 maximum electrons, and there happens to be 14 columns there. So how do we get the principal quantum energy levels? They're going to be represented by the rows. You need to number your rows 1 through 7, and those are going to be your energy levels. Let's look at doing an electron configuration for carbon. We're going to start here at quantum energy level 1 and read it across like it's a book. In this first area, you're looking at the intersection of the column, and remember we said all column 1A's will end with an S1, and lining it up with the energy level, quantum energy level is 1, so this is a 1S1 area. To get to the 1S2 though, this is the only exception. It's helium over here. That is your 1S2. I'm going to keep a book treat. I'm going to keep track of what we're writing down here. We did 1S2. If we stopped there, we would have written the electron configuration for helium. Let's go to the second energy level. Again, this is the S1 column, connects with the second energy level, so that would be 2S1. Beryllium is 2S2. I want to record that down here. This is exactly the electron configuration for beryllium, but we want carbon. So we need to cross the ocean to get here to the P area. This first column is going to be the P1 column, P2. So carbon is 1S2, 2S2, 2P2. Let's look at doing magnesium. It's down here in the third energy level. Again, we're going to start here at the top at the first energy level. And remember, read it like a book going from right to left. We have the first column is first square is 1S1. Helium would be 1S2. Record that. Go to the second energy level. First column is 2S1, 2S2. Record it. Cross the ocean to the P area and you'll get 2P1, P2, P3, 2P4, P5, P6. Record it. That's the electron configuration for neon. Need to go to the third energy level. And again, we're back in the S area, be 3S1, 3S2. There's the electron configuration using the periodic table shortcut method for magnesium. Notice every shape, sublevel, has a quantum energy level in front of it with a superscript. I did not write 1S2, 2S2, P6. I wrote 2S2, 2P6. Let's look at doing a harder one. Remember your areas of your periodic table. we're going to do copper, and we have 4 energy levels to go through, so they can get kind of long. Again, we have 1s1, 1s2. We're at helium. Let's go to the second row here. Lithium is 2s1, 2s2. We record that. And we're doing our P's here. And remember, it goes through 2p1 through 2p6. Third energy level, or third row. Again, start over at 3s1, 3s2. We're going across the ocean to the P's, but we're in the third energy level, so it's 3p1 through 3p6. So we are recording all of the third energy level row. Down to the fourth energy level, we're at 4s1, 4s2. When we get into the D area, even though it's in the fourth energy level, they run 1 row behind. So this would be the 3D area in the fourth energy row. So this would be 3D1, 3D2, count your columns all the way till you get to 3D9, which is copper. So this is copper's electron configuration. But if you take a look at it, what's circled here is the electron configuration for argon. I'm going to show you a noble gas shortcut way of doing this. The rule is that when using a noble gas shortcut method for writing the electron configurations, go to the previous noble gas to the element that you are doing. Remember, noble gases are in this column. So argon comes before copper. So this is argon's electron configuration. Instead of writing all of this, I can represent this section of copper as brackets of argon, and then continue to add the electrons that come after that until you get to your element. So copper's noble shortcut is argon. I need to add these electrons to get there. So that would be 4s2, 3d9. Let's look at doing arsenic. Again, know your areas of your periodic table. Arsenic is over here, and we're going to do the noble gas shortcut method for arsenic. And it would be argon, and we need to add all of these electrons to get to arsenic. So we're in the 3D area. It's going to go through 3D1 through 3D10. And then when we get back to this P area, it goes back up to the fourth energy level. It's only the D's that are affected by running 1 number behind the row. We are not doing any F electrons. When we stop at the arsenic, we write our electron configuration using the noble gas shortcut method. Let's look at doing one for carbon. Go to the previous noble gas, which is helium, and add the extra electrons after that. 2s2, 2p1, 2p2. Magnesium. Previous noble gas that comes before that is neon. The extra electrons that I need to add beyond that would be 3s1, 3s2.